Let's now proceed to section 3.4, concavity and the second derivative test. In this section here, we will determine intervals for which a function is concave upward or concave downward. So we will define what concavity is, and then we will find any points of inflections of the graph of a function, and then apply the second derivative test to find relative extrema of a function. So to begin with, let us define what concavity is. Now, in the previous sections, we have seen that locating the intervals in which a function is increasing or decreasing helps us to describe the graph of the function. Now, in this section, you will see how locating the intervals for which the first derivative increases or decreases can be used to determine where the graph is concave upward or concave downward. So what does it mean to have a graph that is concave upward on an interval? Now suppose you have a function that is differentiable on an open interval I. The graph of the function f is said to be concave upward on that open interval when the first derivative is increasing on the interval. And it is said to be concave downward on I, or on that interval, when the first derivative is decreasing on the interval. Okay, so what does that mean? It means when you say that a function f prime is increasing, that means that the first derivative is positive on that interval. Okay, and the derivative of the first derivative, so meaning to say the second derivative, is positive on that interval. And also when you say that a function is decreasing, that means that the derivative of that function, in this case it is f prime, so the derivative of f prime, so that means the second derivative of the function f of x is less than 0 on that interval. Now, to better understand this definition, we will look at the graph here. Let's look at the graphical interpretation of concavity. Now, if f is differentiable on an open interval I, now if the graph of the function f is concave upward on I, then the graph of f lies above all of its tangent lines on I. So if you look at this one, this is a graph of a function that is concave upward. If you see here, f prime is increasing, and the tangent lines are all below the curve, or the graph of the function f lies above all of its tangent lines. So you see here, these are all the tangent lines, and they're all below the graph of the function. Now, if also the function is concave downward, the graph of the function f is concave downward, then its graph, as you could see here, the graph of f lies below all of its tangent lines. So these are all the tangent lines, and the graph of the function is below the tangent lines. So all of the tangent lines of a function that is concave downward, the tangent lines are above the graph of the function. Whereas if the function is concave upward, the tangent lines are below the graph of the function. And moreover, for this graph here, we have concave upward, and the first derivative is increasing. So if you see here, we have, when you say first derivative, that is the slope, right? So the slope of the function here is, it's actually negative because it's leaning towards the left. So for instance, this is just negative 1/2. And now, the second point here, the f prime on this point here is now a positive number. So for instance, this is 1 equal to 1. And this one, it becomes steeper, okay? So the y values is higher, so the value for f prime also becomes larger. So see here, you have, for instance, this is equal to 2. So from negative 1/2, it became 1 and then 2. So we say that the function here is increasing, okay? So the function f prime, or the slope here, is increasing. So we have f prime is increasing because the slope from negative 1/2, it goes to, from negative 1/2, then it goes to 1, then it goes to 2. As you can see, that the values are increasing. And also here, in this example here, for instance, we have f prime here equal to 1/2, and then here it's now negative because, well, here you have a graph that leaning towards the right and now towards the left. So we have here, for instance, the slope here is now negative. So this one, for instance, is negative 1. And then this is also equal to, for instance, negative 2. Now, in this case here, we could see that the function f prime of x, okay, or the slope here, in this case, the slope of the tangent line here is decreasing. Now, as I've mentioned a while ago, if we have a function that is concave upward, if f prime of x is increasing. So when you say f prime of x is increasing, meaning its slope, its derivative is greater than 0 at that point. So it's positive. So for instance, if I'm going to let g of x, I'm just going to let g of x be equal to f prime of x. I would say g of x is increasing, okay? G of x is increasing if, so g of x is increasing if its derivative is greater than 0. Okay, so if I'm going to take the derivative of g of x, that is just the derivative of the first derivative. So that is just the second derivative. So when you say the second derivative should be greater than 0. Okay. Oh, here, sorry. This is g prime of x is greater than 0. So therefore here, this one is greater than 0. That means to say that it should be positive. Okay, so the second derivative is positive. So this one, to summarize this, we have theorem 3.7. So it says here, if the second derivative of the function is greater than 0 for all x on the interval, then the graph of the function is concave upward. Similarly, if we do the same thing here, if f prime of x is less than 0, negative, that means that the function f is concave downward on that interval. Okay, so it should be negative for all x on that interval. And then if the second derivative is negative for all x on that interval, then the graph of the function is concave downward. Now, so to apply theorem 3.7, we will just extend what we've learned or what we did for the first derivative test in the previous section. So to do this, we first locate the values of x for which the second derivative is equal to 0 or the second derivative does not exist. These are the critical numbers, okay, of the first derivative. And then we will use these x values to determine the test intervals, and then finally test the sign of the second derivative in each of the test intervals. Now, To illustrate, let's look at these exercises here. Let's begin with exercise number 1. So in here, in exercise 1 and 2, the graph of the function is shown. You state the signs of the first derivative and the second derivative on the interval 0, 2. So you look at this interval here. Now for number 1, okay, let's begin with number 1. The graph of the function here, this function here is actually increasing. See? Increasing. So you remember the definition of increasing? So you start from left to right and then you look at the y values. Okay? So for instance, if you have a point here, okay, that would correspond. Okay, so if I have a point here, it would correspond to a point here. And then a point here would also correspond to a point here. So as you could see, if this is my x sub 1 and this is my x sub 2, we have f of x sub 1 is less than f of x sub 2. And that is actually true for any x sub 1 and x sub 2 on the interval. Okay, so this is true for any x sub 1, x sub 2 in the interval 0, 2. So therefore here we know that the function f is increasing. Okay, so since the function here is increasing, therefore we know that f prime is greater than 0, because from here we know that the function f is increasing. That means that the sign of the first derivative on this interval is greater than 0. And also from here, by just looking at the graph, this function here is concave downward. That's concave downward. So here f is concave downward. So since f is concave downward, therefore we know that the second derivative, the sign of the second derivative will be less than 0 on this interval here. Similarly, for number 2, if you look at number 2, this function here f is decreasing. Okay, but just looking at the graph, we know that the function f is decreasing. So since f is decreasing, therefore, first derivative is less than 0. And then the graph also is concave upward. F is concave upward. So, therefore, this implies that the second derivative is greater than 0.